This video is going to cover Section 2.6, Rational Functions, and the target is that you can graph a rational function, label the intercepts and any key points, and then also state the domain and range. A rational function is a quotient of two polynomials. So here's an example. F of x equals 2x squared plus 5x minus 3 divided by x squared minus x minus 12. So this video is going to cover the 10 steps to graphing a rational function, and then it's also going to cover writing an equation of a rational function. And so here is the first step. It says determine the horizontal asymptote. So there are three different cases that you can have a horizontal asymptote at. The first case is you have to compare the degree of the numerator and the degree of the denominator. And so if the denominator has a higher degree or a larger exponent than the numerator, then a horizontal asymptote occurs at y equals 0. The second case is if the numerator and denominator have the exact same degree. So if it's a third degree polynomial divided by a third degree polynomial, then the asymptote is going to occur at the ratio of the leading coefficients. And then the last case is if the numerator is 1 degree larger than the denominator, then you're not going to have a horizontal asymptote. You're going to have what we call a slant asymptote. And so then you just do the division, the synthetic division, and the asymptote is the quotient, and it would be a diagonal line instead of a horizontal one. So using this example of a rational function, we're going to graph it, and I want you to follow along with the steps and with the graph on your notes to graphing this rational function. So first step was to determine the horizontal asymptote, and so you need to compare the degrees. So if you look at the numerator and you look at the denominator, they're both in standard form, and the degree of each one is a second degree. So therefore we're talking about case 2. And the horizontal asymptote is going to occur at the ratio of the leading coefficients. And what I mean by that is just bring out the 2x squared over the x squared and then simplify it, and you're just left with 2. So we have a horizontal asymptote at 2. If this had been 2x squared, etc. over 3x squared, then the horizontal asymptote would have occurred at 2/3. So on your graph, you want to draw a dotted line at y equals 2. So we are going to have a horizontal asymptote at this graph. Remember, an asymptote is a line the graph gets close to but never touches. The second step is that you want to factor the numerator and denominator as much as possible. So this is where your practice of factoring is going to come into play. You're either going to do your diamond or your box, whatever you need to do to get this broken down into parentheses that say like x plus 3 and x plus 4 or 2x minus 1, etc. So when we factor this, the numerator is going to factor to 2x minus 1 and x plus 3. Now I don't have my work shown, but if you want to try this on your own and then just use the video to check your work, you can do that. So the numerator factors to 2x minus 1 times x plus 3. And then the denominator, what two numbers multiply to -12 and add to -1, you get a -4 and a +3. So the denominator factors to x minus 4 times x plus 3. The third step is to find restrictions on the domain by setting the denominator, the bottom, to not equal 0. So we did this a lot in Chapter 1. So here's my rational function. So because I can't divide by 0, I can't have x values that are going to make the bottom 0. So I do x minus 4 times x plus 3 cannot equal 0. And zero product property tells me that x cannot be 4, because that would make this bottom 0, or a -3. So these are the domain restrictions. The next step, step 4, is to cancel out any factors that occur on the top and on the bottom. So we have our factored version of our rational function, 2x minus 1 times x plus 3 over x minus 4 times x plus 3. And so we have two factors of the same that are on top and bottom. I can cancel those out. You can only do this when you are multiplying. So we can cancel out x plus 3's. And then my new rational function, this is called the canceled out version, or you could also call it the factored out version. So my rational function is now simplified to 2x minus 1 over x minus 4. our domain restriction is still going to be the same. You can't have 4 be x or -3. The fifth step is to find any vertical asymptotes that occur in the graph, and this is going to occur at the x value that still makes the denominator 0. So our domain restrictions before was that x can't be 4 and -3, but now we've thrown out the x plus 3 factors. And so our vertical asymptote is going to occur at the x value that still makes the denominator 0. Therefore, we're going to have a vertical asymptote at x equals 4. So I'm going to add that to my graph, draw a vertical dotted line at x equals 4. And once again, this asymptote, the graph is going to get close to, but it's not going to touch. The sixth step is to find the x-coordinate of any holes. A hole occurs at the domain restriction that is not a vertical asymptote. A hole in the graph is just going to be a point that you have to draw a little circle that the function cannot occur there because it would make the denominator 0. So in our factored out version, we have that f of x equals 2x minus 1 over x minus 4. Vertical asymptote occurred at x equals 4, so that means the x value of the hole is going to be a -3. The seventh step then is to find the y value of the hole, and this is how you plug in the x value of the hole into the canceled version of the equation. And so I'm going to plug in a -3 in for x and solve. So I get 2 times -3 minus 1 over -3 minus 4. That simplifies the -7 over -7, which is just 1. Therefore, I'm going to have a hole in the graph at -3, 1. And so you'll see I have a circle with, it's like an open circle. If you remember from domain and range, if you have an open circle, it means it doesn't include that point. And so this is what a hole looks like in the graph, and we'll keep adding to this to get the final graph. The eighth step is to find any x-intercepts by setting the numerator equal to 0, and this is still using the canceled out version. So the numerator is 2x minus 1. I'm going to set that equal to 0 and solve for x. And when I do that, I get x equals a positive 1/2. And so this is my x-intercept. So I'm going to add that to my graph. I'm going to plot a point at 1/2, 0. There's my x-intercept. The ninth step is to find the y-intercept. And you do this just by plugging in 0 for x into the entire canceled out version of the equation. So here's my 2x minus 1 over x minus 4. Plug in 0 for x. You're going to get -1 over -4, which reduces to a 1/4. So therefore, I'm going to plot that on my point, on my graph. I have 1/4 right there on the x-axis, the y-axis for my y-intercept. And then the 10th step is to connect the dots. Now, these are going to look like hyperbolas. So if you remember from Algebra 2, a hyperbola is two curved parts that are separated by two asymptotes, a vertical and a horizontal asymptote. And so I did this as best I could with my mouse. So you'll see this part of the hyperbola, it comes up through the x and y intercepts, gets close to the hole, kind of jumps over it, and then just keeps going. This will never cross the horizontal asymptote. And then you're going to draw the other part of the hyperbola in the opposite corner, or the opposite quadrant. And so it doesn't matter what points. These are all just rough sketches. And these are the only rational functions we are going to draw. We're going to keep it nice and simple because we don't have a lot of time. But we're just going to draw hyperbolas that might have a hole in them, or just a horizontal and a vertical asymptote. So I have the second example for you to try on your own, x squared plus 8x minus 20 over x squared minus 4. I want you to follow the 10 steps and come in on Monday with this done. I'll try it out and I will go over it in class on Monday. The last part of section 2.6 is writing a rational function equation. So let's say I give you, the x-intercept, a root and an x-intercept are the same thing, a hole and a vertical asymptote on the graph. Then you have to come up with the equation. So there are 3 simple steps. The first one is to write the factored form of the rational function using the following pattern. So you can use whatever I give you as the root, so x minus the root, and then on the numerator x minus the x value of the whole. On the bottom you'll have x minus the vertical asymptote times x minus the whole. The second step would be to FOIL and box the top and the bottom. And then the third step is if there is a horizontal asymptote, multiply the top value by the multiply the top by the value of the asymptote. So 3 simple steps. I'm going to go over 2 examples with you. I'm going to leave the third one for you to try on your own. Bring it into class on Monday and we'll go over it. The first example, it says write the equation of the rational function with the following. It has a vertical asymptote at x equals -1, a root at x equals 3, and a horizontal asymptote at y equals 2. So using that pattern, if I have a vertical asymptote, that means I'm going to have it on the bottom. So I'm going to have x minus a -1, which turns into x plus 1. And then I have a root at x equals 3, so x minus 3 on top. Here is my rational function. I don't have a hole in this graph because I didn't give you one, so don't assume anything. And then I told you that the horizontal asymptote occurs at y equals 2. That means I'm going to multiply the top by 2 and then distribute. So here is the rational function with these 3 conditions. If I had said the horizontal asymptote occurred at 2/3, we would multiply the top by 2 and the bottom by 3. Example 2, it says write the equation of the rational function with the following. A vertical asymptote at 3, a hole at x equals -2, and a root at x equals -4. So following that same pattern of x minus root times x minus hole over x minus vertical asymptote over x minus hole, I'm going to have x plus 4, that's the root, so x minus a -4 becomes x plus 4. If there is a hole at x equals -2, that's going to be on top and on bottom because that's what we canceled out when we were graphing, so x plus 2, top and bottom. And then there was a vertical asymptote at x equals 3, so I'm going to plug in x minus 3. Then box or FOIL those together, and you get x squared plus 6x plus 8 over x squared minus x minus 6. I didn't give you any more information about a horizontal asymptote, so you don't have to do any multiplication with these. And then the third example is to write the equation of a rational function with a vertical asymptote at 6, a hole at 5, a root at -4, and a horizontal asymptote at y equals -3. Try this one on your own following those 3 simple steps and bring it into class on Monday, and we will go over it in class on Monday. So this video covered section 2.6 rational functions. It just covered the basic graphing a rational function, labeling intercepts and key points, and then the domain restrictions are in the steps, and then the range would just be all y values not equal to whatever the horizontal asymptote and the whole value would be. So we will cover more of these in class on Monday and Tuesday.